So, what we saw in the previous class was that we have an electrolyte interface, and when you have a metal immersed in solution, it forms what is called double layer, and you have a potential drop across the double layer. When you want to measure the potential, you can measure it only across two electrodes. You can't measure the potential drop across a single electrode. And whenever we want to measure the potential, or whenever we want to control the potential, we want to make sure that the changes in the potential occur at the working electrode, the electrode of our interest, which means the second electrode has to be an electrode where the potential drop does not change. So, we have special electrodes called reference electrodes. So, we use the reference electrode and the working electrode, and the reference electrode should offer low resistance or low impedance, and in addition that should not change in the potential. So, whenever current comes through, we need to collect the current in a third electrode called counter electrode. So, normally we use a 3 electrode cell for the electrochemical studies. We also saw that we use supporting electrolyte to minimize the resistance of the solution, called solution resistance. And at that level, I think we left it saying that we have to consider cases where you have flow, mass transfer effects. We have to consider the case where the potential changes the rate constant. So, if I give you an example of how the electrochemical current changes with potential, you visualize this situation. You have a metal on one side, you have a solution on the other side. The reacting species comes from the solution, diffuses, comes to the metal, reacts. The products that are formed, it may be a solid formed on this, or it may be diffusing out in the solution phase. Okay. So, it has to diffuse, come in, react, and then go out. If I give low potential, then the reaction will be slow. Diffusion will be faster compared to this. So, the net reaction rate is controlled by the kinetics. If I give large potential, reaction rate will be very fast. When you have a fast reaction, mass transfer becomes the rate limiting step. That means you consume the reactant A, then the reactant A concentration at the interface becomes very low, the product concentration will become very high. Diffusion from the boundary layer becomes the rate limiting step. Beyond the boundary layer, we assume everything is well mixed. If you look at the current will be low at the lower potential, and in this region we call it as kinetic control. When you go to very high potential, it is going to be diffusion control, and in between where diffusion and kinetic play a significant role, we call it as mixed control regime. Okay. Later when we go into the impedance with diffusion effect, I will also show you how you can derive this expression for this current. Now, how does the potential change the rate constant? When we change the potential, we apply for example 0.1 volt with respect to the equilibrium potential or with respect to the open circuit potential. Not all the 0.1 volt will go in helping the reaction go faster. If you have a reaction where Fe2 plus gets oxidized to Fe3 plus, it does not happen in one step. Normally we believe that it goes through a transition state, it goes to an excited state, and from that it goes to the final state. Okay. So, if I show this example, O is the reactant state, Q is the product state, and the transition state is given by T, and when I do not apply any potential, O, T, Q is the pathway, and the y axis is for the Gibbs free energy. Okay. If I apply the potential del E, the transition state does not remain at the original place, it also shifts. At the higher potential, the transition state also moves, the product's Gibbs free energy state also moves. So, what happens is they do not move to the same extent. Okay. So, they move to a lesser level, and that is given by a fraction called alpha. It is called charge transfer coefficient. It lies between 0 to 1. Best case, T will not move to T prime, in the sense T and T prime will be the same. The worst case, all the del E will be superimposed here. Now, when I change the potential, this has to go from O prime to T prime and then come to the product of Q prime. So, previously when I did not apply any potential, it has to go from O to T and then to Q. It needed to climb an activation hill. Now, it needs to climb a different activation hill. So, the rate constant is related to del G. Rate constant is given as exponential of del G. Now, I change the del G. Previously it was T minus O. now it is T prime minus O prime. And how much is the change, how much is the difference now is controlled by the value of alpha. So, if alpha equal to 1, we do not have any benefit. If alpha is 0, you get the maximum benefit, because now it has to climb lot smaller hill. Typically alpha is going to be between 0 to 1, and normally we do not know the value of alpha. So, the standard value that is commonly taken is 0.5. To understand what happens in a little easier way, you can look at this scenario where Ag plus deposits from the solution onto the electrode. The electrode is held at ground potential, that is it is at 0 potential. So, Q and Q prime are the same for this electrode. In the solution, Ag plus is solvated, it is in the solution, and by applying different potential, I can change the Gibbs free energy level of this, and only fraction of it goes to the transition state. Therefore, you get part of it facilitating the rate constant, that is part of it is going to help increase the rate constant. This part is going to remain the same, and when you write the equation for this, you will find that rate constant is exponentially related to the potential. So, first part is that mass transfer plays a role, and we have to consider that in most of the cases. We can control the boundary layer thickness by changing the flow rate, by rotating the electrode. Next is the rate constant, kinetics can be controlled by changing the potential, and it is not linear, it is exponentially related. Okay. Now, we will move on to the concept of impedance. You are all familiar with resistor. You have a resistor, you can apply a sinusoidal wave of frequency. In this example, we have seen sinusoidal wave of 1 hertz. The potential here is given by the violet color line, and the current, it is on the right axis. I have not given numbers for that. The magnitude is represented by the maximum or peak value. First point to notice is that when the potential starts at 0, current also starts at 0. When the potential is maximum, current is at maximum. That is, current follows the potential without any phase difference. They are in sync. If we change the frequency from 1 hertz to 3 hertz or any other number, right, in 1 second, in this example, we will have 3 cycles completing. The current value does not change. If you look at the peak value here and the peak value here, at 1 hertz and 3 hertz, peak values are the same. The current is still in phase with the potential. So, for a resistor, the current is always in phase with the potential. The phase difference is 0. The current value does not depend on the frequency. Okay. I also want to show you what happens when you have a capacitor. We also want to see what happens when you have an inductor. These are electrical elements, and later we will see what happens when you have electrochemical reaction. So, in this, current is in phase with potential, and you can get the magnitude of EAC 0 divided by IAC 0, that gives you the resistance, and this is also called the impedance of the resistor, and that is independent of the frequency. We will move on to the next example where you have a capacitor. Again, the potential is given in violet color and the current is given in the dashed line, blue color line. First point to notice is that there is a phase difference. The current starts at 0 here and the potential is at 0 here. So, the current comes actually before the potential. If I take this as a sinusoidal wave, starting here, it goes up and completes a cycle. Potential starts here. So, current actually leads the potential. It comes before the potential. This is after we apply few cycles, this is how it will come. When I start giving the potential here, the current will not start here. Current will also start at 0, but then it will stabilize within a cycle. And afterwards, when I look at the second, third, fourth cycle, starting as time t equal to 0 at the beginning of the second cycle or the third cycle, and then draw the potential, this is how the potential will look like, and this is how the current will look like. So, current will have a phase offset. Second, look at the magnitude here, it is at certain value. If we change the frequency, this is what I would see. I increase the frequency, goes from 1 hertz to 3 hertz. Within a second, I have 3 cycles, potential cycles. Now, I still have 90-degree offset or pi by 2 radians offset. You have 2 pi radians for 360 degree. So, 90 degree will correspond to pi by 2 radians. You also see that the magnitude here is smaller compared to the magnitude here. These are drawn at the same scale, although I have not given you the numbers. So, at higher frequency we get more current for the same potential. So, the peak potential is 0.1 volt here, peak potential is 0.1 volt here, current value is a low value here compared to a high value here. So, first point to note is that current leads the potential by 90 degree. The relationship between the current and the potential for a capacitor is given by the differential equation. So, AC current is given by C is the capacitance multiplied by the derivative of potential with respect to time, and because it is a sinusoidal wave you can write the expression C is the capacitance that will not change for a given capacitor, but whenever I change the frequency I will get a different current magnitude, because when you take the derivative you are going to get the omega out and then sine will become cosine. Sine becomes cosine, you can write cosine as sine with 90 degree offset. So, this shows the relationship between current and potential. This equation gives you for a capacitor how this impedance can be calculated. If I want to calculate the magnitude of the impedance, I have to take it as potential by current, in the absolute value is given by the bars here. I can take the ratio of EIC0 by IIC0. The phase difference is 90 degree, that comes here, current actually leads this, but the impedance is given by 1 by omega c. So, whenever the omega value increases, omega is called angular frequency, whenever the frequency increases impedance will decrease. So, for the same current magnitude you will get more current. Higher frequency it is easier to pass through a capacitor. Infinite frequency it will offer 0 impedance. So, normally resistance is something where we say potential divided by the current will give you the resistance. Impedance is something where you have a potential divided by the current, but you also have to know the phase. So, it has magnitude and a phase. In case of resistor the phase is 0. In case of capacitor or in case of an inductor or in general for a reaction, you will have to expect that the phase may or may not be 0. So, sometimes impedance is called as a generalized resistance, or it is also called as a vector ratio of potential to current. Sometimes it is referred to as transfer function. You give potential, you can calculate the current, these two are related by a transfer function. So, there are different ways of expressing. And the third example is for an inductor. For an inductor there is a phase offset, but it lags behind the potential, current lags behind the potential. So, potential starts here, it goes up and comes down and completes the cycle. For the inductor the current starts with a pi by 2 radians or 1/4 of a cycle later. So, it lags by 90 degrees, similar to capacitor except that it lags here compared to a capacitor in which it leads. And for 1 hertz it has certain magnitude. If we apply 3 hertz the magnitude here actually is lower. So, for an inductor if you go to higher and higher frequency you will get less amount of current. So, here the phase lags by 90 degree or minus pi by 2 is the phase difference, and the relation between potential and current is given by the differential equation, where L is the inductance, that is a constant for a given inductor. If you want to find the current you have to integrate it. Right now we can just get the relationship between potential and current by taking the derivative of the current with respect to potential, sorry, with respect to time, and again you can write the cosine as sine of omega t plus 90 degree, except that now the current lags. You can find the magnitude of E by I, and that is going to be omega L. If I take the equation, rearrange it so that I get E by I, I will get L omega sin omega t plus 90 degree. Phase difference comes here and then the remaining part is the impedance. So, here what it means is for a given inductance, if I ask you this is the capacitor, what is the impedance, you will have to ask me what is the frequency of the wave that you are applying, then I can tell you what the impedance is. If it is a resistor, this is 10 ohm, the impedance is 10 ohms. If it is inductor, I have to tell you the inductance. If it is a capacitor, I have to tell you the capacitance. In addition, you also have to be given the frequency. Now, We usually represent impedance as a complex number. See, we saw the current has a magnitude and phase. If we take the vector ratio of potential to current, that also has a magnitude and phase. Magnitude of the potential divided by the magnitude of the current will tell magnitude of the impedance. Phase of the potential, which is usually 0, because we are applying the potential, we say at time t equals 0, it just starts, therefore phase is 0. Phase of the potential minus the phase of the current will tell us the phase of the impedance. Now, we have two quantities, one is a magnitude, it can vary from 0 to any number, any positive number. Another is phase, which can vary from 0 to 360 degree, which means we can represent this in polar coordinates. We can also represent this in Cartesian coordinates. We can write it as real plus imaginary. Now, do not think because it has an imaginary number there is something unreal about this. It is just a convenient way of representing phase and magnitude in one number. One number here means complex number. So, we can call it as one number. We can also call it as pair of numbers, real part and imaginary part. We can also say it has a magnitude and phase. Okay. So, we use complex number for convenience, not because the imaginary number is somehow unreal in some aspect. Potential, we can write it in the complex form as EAC0 e power j omega t, where j is given as square root of -1. It is an imaginary number, and normally I is reserved for current density in electrochemical impedance spectroscopy. I is reserved for current in electrical circuit. So, we do not want to use I for square root of -1, because in normal complex numbers you will use I for imaginary number, here we use j. Of course, sometimes you will have confusion where j is used for current density. So, in this course we are just going to keep I for current density or current if it is electrical circuit, okay, and j for square root of -1. Now, e power I theta or e power j omega t, you can represent it, you can write it as cos omega t plus j sin omega t. You are familiar with what is called de Moivre's theorem. So, it is possible to write it as sine and cosine. Sometimes it is convenient to use it as exponential, sometimes it is easy to use it as sine and cosine. Whichever way is convenient, we will use it that way. Likewise, sometimes we will use polar coordinate, sometimes we will use Cartesian coordinate. When you have a complex number, if you want to add or subtract, it is easier to do it as real plus imaginary. If you want to multiply or divide, polar coordinates is easier to handle. So, we will just use whatever is convenient to us. Z is normally used for impedance. So, Z subscript R here refers to impedance of a resistor, and that is given by R. Impedance of a capacitor, we would write it as 1 by j omega c. 1 by omega c is the magnitude, 1 by j tells 1 by j is going to be 1 by square root of -1, that is going to be minus I or minus j. That really tells the current is leading by 90 degree, that means impedance is going to have minus 90 degree. Now, if you visualize in the complex plane, you will write it as x axis here, y axis here, this is the real part, this is the imaginary part. Minus j means it is minus 90 degree, plus j means it is going to be on above this real axis, it is going to be plus 90 degree. So, impedance is given by 1 by j omega c, impedance of a inductor is given by j omega L. This is just another way of saying the impedance has a magnitude of omega L and it is going to lag by 90 degree, current is going to lag by 90 degree, impedance is going to have plus 90 degree, because it is potential divided by current for the magnitude, potential phase minus current phase for the phase value. In actual electrochemical impedance measurement, many times we superimpose an AC on top of DC. Many times we will just use an AC, okay. Many times, meaning depending on the type of experiments you are conducting and what you want to measure, you may superimpose an AC on top of DC. If you look at the violet color line, it is just a AC with 0 DC bias. If you look at the blue dashed line, it has a 0.2 DC and 50 millivolts of AC superimposed on it at particular frequency. 1 cycle, 2 cycle, 3 cycle, 4 cycle, 5 cycles in 5 seconds. So, 1 hertz frequency, and you will not get the same impedance value. In a simple electrical circuit, it will not show any difference. When you have electrochemical reactions, when you superimpose a DC and AC on top of DC, you will get a different impedance. Now, another point which is very important, which I want you to note, is that when you use the equipment and measure the impedance, what you measure is actually differential impedance. Okay. Differential impedance means it is dE by di, it is not E by I, and there is a difference. I will show you with an example here. Let us not worry about what type of reaction will give us this type of curve. Let us just say current versus potential. If I draw, it is going to go like this and come down. It is going to increase up to 1 voltage and then it is going to decrease. When you have a metal immersed in a liquid, when you apply potential, it may form a passivation on top of it. So, when you go to higher and higher potential, it may form a passivating layer, which means the current will decrease after some time. Low potential, it may not cover the surface, passivation layer may not cover the surface. You may get higher current as you increase the potential, but beyond a limit it can decrease. So, it is not an unrealistic example. If you take the value of E by I, E here is in 1.5 volts, it is in the x axis, and I is let us say 0.75, you are going to get 2 ohms. If I take the dE by di, the slope here is going to be di by de, correct. dE by di, I am going to get a value of minus 0.33. First point to notice, it is negative, and then the value is different from the E by I value that we got before, because the slope at a particular location is not going to be equal to the value at that location. Slope is different and the value is different, and what we measure experimentally is dE by di, it is not E by I, which means you should not be surprised to see negative values of impedance. We will elaborate more on it when we show example reactions, where we show that if it is this type of reaction, for these kinetic parameter values, you will get negative impedance, and this is the physical meaning of this. So, if I measure E by I, I will have to write E DC plus E AC, because here I will take a DC potential of 1.5 and on top of it we will superimpose an AC, and we will have a current which has a DC value and an AC value. But we are not going to look at E by I, we will only look at EAC by IAC. And there are other terms used. One is admittance, which is basically inverse of impedance. Impedance is denoted by Z, admittance is usually denoted by Y, and some papers, usually the older ones, will use a term called immittance as a common terminology for both impedance and admittance. So, they say we are measuring immittance, unless they really tell you what exactly they measure, it can be either impedance or admittance. Next, when you connect two elements in series or parallel or any other way, we want to be able to calculate the impedance for the entire set. The more general laws are called Kirchhoff's laws. If you look at any junction, sum of the current that flows in must be equal to the sum of the current that flow out. Normally, if you just look at two elements, simple cases, whatever comes in has to go out. Okay. Second, if I take a closed circuit, closed loop, and I take the potential algebraic sum, means from going from A to B and then B to A, that has to have 0 potential. So, that algebraic sum of all potentials around any closed loop is 0. That means, if you go from A to B this way or this way, I should have the same potential. If you go from A to B in this way, B to A is going to have the negative value, it has to be equal in magnitude, opposite in sign. Now, most of the time we will look only at elements in either in series or in parallel. Although these laws can be applied even in much more complex situations, we look at cases where they are in series or in parallel. If you have two elements in series, in this example I have R1 and R2. The total impedance I measure between the location 1 and location 2, that is going to be the sum of the impedances here. If I put two elements in parallel, R1 and R2, the admittance has to be added to get the total admittance. So, admittance of R1 is going to be 1 by R1, admittance of the second element is going to be 1 by R2. Sum of this will give us the total admittance. Total impedance is going to be inverse of the net admittance.